Hey, this is the introduction video for Module 5 for Math 85, and this module deals with radicals. And the word radical implies that you'll be dealing with some sort of root, and usually what we think of when we think of roots is the square root, but there's other roots, like a cube root is indicated by that little 3 up there, or a fourth root, or something of the sort. And these poor little roots kind of get left out of the order of operations. You remember order of operations comes from the saying that helps us remember the order of operations, and that saying is, "Please excuse my dear Aunt Sally." And maybe something you haven't thought of is that the operations are grouped together with their opposites. So like addition and subtraction are opposites. Like up here in the example, if you wanted to get rid of addition, you just subtract both sides. And that reminds us that addition and subtraction are opposites. Likewise, multiplication and division are opposites. So if in the second example, x is being multiplied by 2, simply divide by 2. And that undoes the multiplication. And do it to both sides to find the value. So that reminds us that multiplication and division are opposites. But how about exponents? What's the opposite of exponent? Doesn't seem like it has one. Well, the opposite of an exponent is a root. So, for instance, if I wanted to undo a exponent of 2, I would do a root 2, or a square root. And in this case, it's understood to be a square root if there's no number up here in what they call the index. We'll talk about the index later, but see how there's no number right there? The little number that I referred to earlier, I must have erased it, but there's no little number up there, so it's implied that that's a square root. So to undo a square, I did a square root, and look what's going to happen. The square root and the square cancel, but you have to do it to both sides, and then that tells me that the value that makes the equation true is going to be the square root of 9, which is 3. It also ends up that you could also use -3 as well. So the moral of the story is that exponents do have opposite operations, and their opposite operation is roots. So the opposite of a square is a square root. The opposite of x cubed is a cube root. The opposite, of course, of x to the fourth is the fourth root. So that's important as you go through this module. Earlier I was saying that if there's no index, it's implied that you're dealing with a square root. Now the index is found by the little number up towards the top left. That number is called the index. And the actual symbol there is called the root. So a lot of times it's called the square root if you don't see an index, or a cube root if the index is 3. And then the number inside the root is called the radicand. So just some terminology. And what a root tells us, in this case the first example is a square root, it actually asks a question. It asks, what number squared gives me 16? What number squared gives 16? And of course the answer is 4. 4 squared gives us 16. So the square root of 16, the answer is 4, because 4 squared gives us 16. You can see how squares and square roots are related. This, of course, asks, what number cubed gives us 8? What number cubed gives us 8? So what times what times what? What number cubed? There. That's what it means to cube. That means something times itself 3 times gives us 8. Let's see. I think 2 does, right? 2 times 2 times 2. That's 2 times 2 is 4, times another 2 is 8. Yeah, so the cube root of 8 is 2. Now we can use this fact to simplify things that aren't perfect squares, or the inside radicand isn't a perfect square. So what we can do is we can simplify by trying to see if any factors are perfect squares. So what you're going to do to simplify a square root that doesn't seem like it can simplify, because nothing squared gives me 20 exactly, well, what you do is you create factors again. There's that word factors. We create factors, in this case, by using a factor tree. And factor trees are created by looking at any two numbers that multiply to give you 20 other than 20 times 1. So I'll go, I don't know, 2 times 10, I guess. I could go 4 times 5 if I wanted to. Let's see, two numbers that multiply now to give me 2 are, well, other than 2 and 1, there's none, so I'm going to go ahead and circle that. How about any numbers that multiply to give me 10? There's 2 times 5. Now what I want you to do is, I just want you to consider the numbers that are circled, and then rewrite the square root of 20 as multiplication of those numbers that are circled. So 2 times 2 is 2 squared times 5. Well, now look what we got inside. We have a square. You see, we have a square. And what's the opposite operation? A square root. So now the square and the square root can cancel each other out and just leave you with the base 2 on the outside. Now you might say, now wait a minute, where did the square go? And how come it's not inside the square root? Well, the square was canceled by the square root, and now you can see that it's free because the square root got canceled with the square. Look at base 5 here. Base 5 does not have a square, so it does not get canceled out of the square root. So because base 2 had the exponent of 2, the square undid the square root, and we could simplify the square root of 20 as 2 square root of 5. That simplification process is going to be really helpful, especially when it comes to things like this, where they ask you to add square roots. And adding square roots, that brings us back to a concept of like terms. If you remember, you can only add like terms if they have the same variable. Remember this? So in this case, the first and third term were like, and you could add the coefficients together. The coefficients were 2 and 4, so we could add those together and give me 6x plus 3. Well, in this case, we have coefficients, and they have to have the same radicand. In other words, inside the square root. And right now, it doesn't seem like they do. But we got to be a little bit more persistent and see if we can't simplify the inside. Look at the first term. The first term here, could we factor tree? No, I don't think we can factor tree 2. He's done. I'll just rewrite it to remind me that he's done. How about 8? Oh, there's 4 times 2, and then we could go 2 times 2. So this guy actually is 6 times the square root of, remember, we're looking for squares to undo the square root. So I guess I could write 2 to the third, right? Because there's 1, 2. I could do that, but that wouldn't be helpful because I'm looking for a square to undo a square root. So I'll go 2 squared, that takes care of 2 of them, times 2. You see that? I'm hoping that I see that square so that the square root can undo the square. So it does its job. The 6 stays on the outside. Now this base 2 can come on the outside because the square root undoes the square. This poor little 2 has to stay inside because it didn't have a square. Now I can multiply 6 times 2, which is 12, and that poor 2 on the inside. So now I'm looking at 12 square root of 2. Now look, now we have like terms because they have the same inside the square root. And now I can just add up the coefficients. 4 plus 12 is 16. They both have square roots of 2. If they didn't have square roots of 2, I couldn't add them together, but they do. So that's the result. They have to have the same insides, and you get the insides by simplifying. Now the nice thing about this idea of squares and square roots being opposite is they can help you solve equations. Like if you want to look at this equation, to get rid of that square root, you probably know what I'm going to do. Square it, right? Because that's the opposite. But do it to both sides. Square both sides of the equal sign. Now what happens on the left is the square root and the square cancel, just leaving you with the inside x plus 2. On the right, 5 squared, there's no square root to cancel, so 5 squared is 25. And now it brings me to a nice little linear equation. If it was quadratic, you would know what to do, right? Set it equal to 0, factor, and then set the factors equal to 0. But this is linear. So throughout, you can kind of see what's going on is that we're always trying to get our equations back to something that's linear. Remember with our fractions, those things called rationals? Rationals, what we did was we tried to get them to be something that was quadratic. We usually did that with cross multiplication or with common denominators, and then from quadratics we can factor and get to something that's linear. But always getting to something that's linear. Same thing with what we're doing in this module. Radicals have to get to something more simplistic. Maybe it might be quadratics. A lot of times that's the case because you're going to be squaring both sides. But you know how to deal with quadratics, right? You factor them, and then the reason why you factor them is so that you can, I do like linear, but that's not what I meant. You can eventually get them to be linear. After you square both sides and factor, you can eventually get it to linear. So it's always trying to get things back down to linear equations because linear equations are easy and we can do it. So I hope this introduction video helps, and good luck on this module.